what we're doing today, we're going to look at some completely different kinds of numbers that you've never, ever seen before. Every number that you've ever dealt with in your life has been a real number. We've taken the real numbers, and earlier in the year, we broke those down into subsets of the set of real numbers. Remember, we said that all real numbers are either rational or irrational, right? At the very beginning of the year, we talked about this stuff. The rational numbers are all the real numbers that can be written as fractions. The irrational numbers are all of the real numbers that cannot be written as fractions. Fractions of where I have an integer divided by an integer, right? The rational numbers, if we write them as decimals, do you remember what they do? The rational numbers? They either repeat or they, like for example, 1/3 would repeat. It would be 0.3 repeating forever. But what about 1/4? What's that? Say it again. 0.25 stop. That's it completely, right? So it terminates. The decimal terminates. Rational numbers always either repeat with a pattern or terminate. Irrational numbers don't do either, right? Irrational numbers just are random. They just go on forever with no pattern, like pi or the square root of 2 or something like that, okay? And then we even took the rational numbers and we broke those down into some smaller subsets, integers and whole numbers and natural numbers. We did a bunch of stuff with these real numbers. We sliced and diced them a bunch of ways. Today we're looking at a completely different set called imaginary numbers. Completely different. They're separate from the real numbers, okay? Why do we need these things? Well, we need these things because what if we want to solve an equation like, I'm going to skip ahead just for a second, like that. What if I want to solve that equation? Okay, this is good review for people that want to do a retake on the test. If I'm doing a problem, if I'm trying to solve an equation like this, what's my strategy? Do I need to factor? Yes or no? I do not. You're right. Don't need to factor. It's easier than that, right? What do I do here? I add 5 and then no, okay. That's where a lot of people this test went south on them there. Then I would divide by -2 and then I would square root. Okay, but either way, we'll go through all the steps to help, people that are having a little trouble with that, help them iron out their difficulties. But the point is, I can isolate x here, right? That's what's different about this one. I don't have to factor this. I can just isolate x because this is an example of a problem where I can point to a single x. And what have we always said? If I can point to a single x, I can isolate it using inverse operations, right? So we can take PEMDAS and just go backwards through PEMDAS to isolate x, right? So the first step then would be, and we got to follow these in order. People tended on the test, they tended to mix these two up. That's what you were doing, Gabe. You're mixing those two up. It's easy to fix though. We're just going to start at the bottom and work our way up. Well, what's first step? First step is add or subtract. Okay, so we're going to add 5 to both sides, and that's going to give us -2x squared equals 18. We work our way up the ladder here. So next step would be multiply or divide. Well, I got to divide by -2. So those guys cancel, right? And that gives me x squared equals 18 divided by -2 is -9. Okay, what's the next step? Square root. Okay, so finally we get up to the square root, don't we? So here's square root. So I'm just going to square root both sides. I'm going to get x equals, I have to include a plus or minus, don't I? Because I'm square rooting both sides. The square root of -9. Uh-oh. What's wrong with that picture? What's wrong with that? What have we always said about, there's 2 rules for real numbers. We can't ever divide by what number? I can divide 7 by anything except, what can I not divide 7 by? No, I can divide it by anything except, no, I can divide 7 by -1 is -7. I can do that. What number can I not divide by? 0, right? There you go. I can't divide by 0. That's something I can never do. And the other rule we had was we can't take a square root of a negative number, right? And that's true for real numbers. So look, I've got a negative number inside my square root. So the answer has always been no real solutions, right? That's what we would have said in the past. Okay, but there are solutions. They're just not real. There are solutions, and the solutions involve imaginary numbers. So let's talk about these imaginary numbers. And by the way, imaginary is a really bad word here. It's really misleading because doesn't it make it sound, you tell me, I've got real numbers and then I've got imaginary numbers. Which one sounds more concrete and useful? The real numbers. We don't need to worry about these fluffy imaginary numbers, right? They're just imaginary. That's a really bad name because they're not. They're not imaginary. They're just as real numbers. They just do different things, as we're going to see. The numbers that we've used, real numbers, at some level, real numbers, what they do is they count things. They're about cardinality. Even algebra, if you really slice it and dice it, you'll see that everything we do is about counting stuff, grouping things, okay, into numbers of things. Imaginary numbers just do different kinds of things, but they're just as useful. My background I've done a lot of math, but my background is technically in physics. And I was an electrical engineer before I started teaching. And the stuff that I did before I taught math, we used imaginary numbers more than real numbers, honestly. When you're doing like electronic stuff, you use them all the time. So I'll show you some examples of, once we get into them a little bit, I'll show you some interesting examples about ways that these things can be useful to us. But you're just going to have to believe me for now, that even though they say they're called imaginary numbers, they are very important in math. Okay. All right, so what are they? Well, the imaginary unit, the real unit, by the way, is the number 1. Okay, when we say unit, it means equal to 1. So the real unit is 1. We always measure things in increments of 1, don't we? Right? The imaginary unit is something different. It's called I. Okay, and I is the solution to this equation up here. X squared plus 1 equals 0. If I solve that equation, look what happens. I'm going to take this equation right here, and let's go over here and solve it. I would just subtract 1 from both sides, and I would get x squared equals negative 1, right? And so when I square root both sides, I would get x equals plus or minus the square root of negative 1. Well, we define that square root of negative 1 as the imaginary unit. And so our answers just look like x equals plus or minus I. Okay? So the square root of negative 1 is what I is defined as. That's what it's equal to. Okay? So this is how we're going to deal with square roots of negative numbers. We're always going to get i's in our answer. Okay? So a pure imaginary number is one written in the form some number b times I, where b is actually a real number and I is the imaginary unit. Okay? So this would be like b could be 5, for example, and we'd have the imaginary number 5i, or it could be negative 4i, or it could be pi times I. Okay? All right, so let's practice this a little bit then. Let's simplify some negative square roots. Okay, and this, you're going to see this is really not that big a deal. Okay, how about this guy here? The square root of negative 9. So we've got a property here, first of all, that I want you guys to remind me about. You already know how to use this. Like if I had the square root of 2 times the square root of 3, what square root is that also equal to? The product of the square root of 2 times the square root of 3. The square root of what? 6. Yeah. That's equal to the square root of 6. Okay? So what is, for example, the square root of 14? I could write that as what then? Give me a product of 2, square root of 2 times the square root of 7. Good. And this would be a useful one. How about if I had the square root of 18? What would I probably want to break that one into? I could do 6 and 3. What might even be a better idea, though, if I wanted to simplify this? How about 9 and 2? Square root of 9 times square root of 2. And the reason being, because if we were doing couples go out, singles stay in, I'd get a couple of 3s out of that 9, right? So then that ends up being 3 times the square root of 2. So we've already done a bunch of stuff like this. We already know we have a rule that says the square root of a times b, of a product of two numbers, we could break up into the square root of a times the square root of b, right? No big deal. So the square root of 9 then, we could write this as the square root of negative 9, I'm sorry. We could write that as the square root of 9 times the square root of negative 1, agreed? Okay, well, what's the square root of 9? 3. So we're getting 3, and what's the square root of negative 1? That's I. Every time, that's just I. So can we take a shortcut there? Yeah, we kind of can. Anytime we're taking a square root of a negative, all we have to realize is that the fact that I had a negative inside the radical is eventually going to turn into an I outside of the radical times a regular square root. Everybody get that? Okay. So how about the square root of negative 5? Well, the fact that I've got a negative inside means that I'm going to get an I outside. And what about the square root of 5? Can that be simplified? No, it can't be. So my final answer in this case is just the square root of 5 times I. That's my answer. That's all I can do. The only thing I can do in this case is get turn the negative part into an I. That's it. Now, a lot of times mathematicians will write this seemingly backwards. They'll put the I in front of the radical. You don't have to do this, but why might that be a good thing to do? Say that one more time. Okay, the number in front of the radical is the couple part. There's even a simpler reason for this one. If I write the I after the radical, how could that potentially be confusing? Oh, it could look like it's under the radical, right? So a lot of times we write things in front of radicals when we're multiplying them instead of behind, just so we know that they're not actually inside the radical. You don't have to do it that way. You can be careful and just write it outside, but you'll see that a lot of times in math books, okay? All right, so let's try square root of negative 32. And let's do a little board work. We have such a small group. The pens have already been sterilized. Everybody come up and grab a Kleenex to wipe the board off and just spread yourselves out at the boards. And let's try a little bit of this here. We'll do a little board work on a Friday. Okay, and the online folks, you guys can just be doing this on a piece of paper, it's fine. So we want to simplify the square root of negative 32. So this is really just some good practice at simplifying radicals, right? Because the imaginary number part's pretty simple. Okay, so try that. Try number 5. And if you want to, I mean, this would be a good time when you don't have to write this out like I was writing these as products of square roots. And you can do that, but you can also just use a factor tree and do couples go out, singles stay in too if you want to. Okay, for the 32 part, right? Very good. Good job, McKenna. That's good. You got it. Okay, remember when you factor that thing, you got to group the results into couples and singles, right? There you go. Good. Well, no, those aren't single. The single, we're only counting this stuff at the ends of the branches, right? Where's that 2 outside coming from? Okay, but you got 2 couples, don't you? Well, okay, right, because you have 2 times 2 outside. No, you're right. So you get a 4 outside. Good. Okay, good. You see that, Gabe? Because you have 2 couples of 2. So each couple is going to give you a 2 outside and and then you got a 2 inside because you had a single 2 left over. So there you go. So your answer is 4 radical 2i. Okay. Okay. Yeah, there you go. Good. And you broke that other 4 into another couple of 2s, right? There you go. Perfect. Okay, good. So let's just go through this together real quick. So I'm going to show you, if we take the 32, those are all correct. I could break it down into 2 couples of 2 and a single 2, right? But I can also do this. If I'm taking, I already know that the negative, the new stuff here is, I mean, it's almost nothing, right? Almost the entire problem is just a review of stuff we already know. The only new part is our answer, we're going to get this I outside, but we just have to simplify the square root of 32. So if I make a factor tree, these are all correct. If I were doing this, I would do one thing slightly different. I would break up my 32 into a 16 and 2. How come? Okay, because I'd like my couples to be bigger if I can, right? Then I only have to have 1 couple of 4s instead of 2 couples of 2. So I could do this. I could break that into a 4 and a 4, which is giving me a couple of 4s and a single 2. So I'm getting 4 radical 2i. Everybody agree? Okay. All right. I'm going to show you a little trick here in Desmos for, like, let's deal with, for example, what if we want to do the square root of negative 192? You guys could all do that, but go ahead and drop your pens and come back to your desks for a second. I'm going to show you a little trick. This is a good trick. So if I want to simplify the square root of 192, because I know that the negative part is just going to give me an I, right? But I've still got to deal with the 192. Okay, in Desmos, and you don't always have access to Desmos, but when you do, this is pretty useful. In Desmos, here are the steps I can go through to simplify this. Okay, in Desmos graphing, the first thing I'm going to do is I'm going to define a function. I'm going to call it f of x, and it's always going to equal whatever the number is I'm trying to simplify that's under the radical divided by x squared. Everything's the same except that number is going to change depending on what your number is, right? Okay, in fact, I think I'm going to go through this like live in Desmos so you can see this happening as we speak here. Okay, so all I do here is I'm doing f of x equals whatever my number is divided by x squared. Okay, and there, we don't care about the graph. You can just ignore the graph. Okay, we're going to make a table out of that. Right, we want to make a table out of that. And the way you make a table in Desmos, it's really simple. Once I've put a function in, I can just go up to that gear up there, and I can choose this option that's convert to table. And then it's going to make a table out of this where the first column are the values of x that I'm inputting, and the second column are the output values of f of x. Okay? And I don't need any negative values. So I could just, if I want to, I could just go in here and delete. If I just hit, if I hit backspace twice, it just deletes those rows. I don't have to do this, but I don't really need those rows. I just want to start at 1. Okay, what's this mean? What do these rows mean here? This means that if I input an x value of 1 into this function, the output is 192. Well, that makes sense, doesn't it? Because 192 divided by 1 squared is 192, isn't it? So what if I input a 2? 192 divided by 2 squared, well, 2 squared is 4. 192 divided by 4 is 48. And then if I just put my cursor next to the 2 and I just hit enter a bunch of times, Desmos knows the pattern I'm following is I'm just going up by 1 every time. Okay. Well, what's this telling me? If I divide 192 by 9, by 3 squared, I get some weird decimal. It doesn't go in evenly. But if I divide 192 by 16, by 4 squared, it does go in evenly. It goes in 12 times, right? If I divide by 5, it doesn't, 5 squared, by 25, it doesn't go in evenly. If I divide by 6 squared, it doesn't go in evenly. If I divide by 8 squared, that's 64. It does go in evenly, though, and so on. I can keep going down the list. But at some point, once I get down there below 2, it's not going to do me any good anyway, right? Because at that point, well, unless, actually, if I get a 1 on this side, that would mean that that 192 is a perfect square. Okay, I'll show you an example of that next. But once I get below 1, obviously I'm never going to find an integer in this column after that, right? Because they're just going to get smaller and smaller and smaller and get closer to 0, right? What's so useful about this? Well, if I know that 4 goes into 192 evenly, that means that 192 is equal to 2 squared, which is 4 times 48, right? Everybody agree? Okay, so if I know that 4 squared, which is 16, goes into 192 evenly 12 times, well, then that means that 192 is equal to 4 squared times 12. It's also equal to 8 squared times 3. That's pretty useful because the numbers in the left column are all going to end up being perfect squares, right? Okay, so then when I make my list, I'm just going to scoot this thing over a little bit. When I make this list, then, this is telling me that the square root of 192 is equal to, this row right here is telling me that it's equal to 1 squared. Well, the square root of 1 squared is 1 times the square root of 192. Duh, that didn't help me, right? But this row right here, I guess I need to go up a little bit with this. So that one went there, okay? This row right here is telling me that it's equal to 2 outside times the square root of 48 inside. Isn't that cool? This row right here is telling me that it's equal to 4 outside times the square root of 12. This row right here is telling me that it's equal to 8 outside times the square root of 3. You get that? That's pretty slick. Because that's telling me, and I know I can't go any further because I could have gone further up here, because if I were to factor these numbers inside the radical, I'm still getting couples out of the factoring, right? But when I get to 3, I'm done. There's no couples in there, so I know I'm done. That's a prime number in this case, right? That's a pretty slick way to do really big numbers. Like, I'm going to give you an enormous number, and I want you to practice this on your Chromebook. So break out your Chromebooks. I want you to try this once. So let's do about... Okay. Try calculating using this trick. I want you to simplify the square root of 3,312. And this is like, if I just put that into a calculator, I'm going to get some weird decimal. That's not what I'm looking for. I'm looking for a simplified version of the radical. So this is where you have to use the Desmos trick. Okay, I'll go through it with you here. You guys do it on your own, and I'll do it on the screen. If you need to look up and check yourself against my work, you can then. Once you've done this once, you don't have to delete everything. All I have to do is just change the numerator. Okay, tell me when you got an answer. Think you do? What'd you get? You got it. Is that everybody got it? Okay, good, good. Pretty good trick I told you, huh? Kind of got to like that. So if we just look at our table here, we can see that this is the last row we need to look at because 23 has no couples, right? So there we go. We can see that this is equal to 12 times the square root of 23. Okay, good stuff. All right, I think we got it. No, that's not all you had got to do on the test. Okay, so going back over here then, what else do we need to look at? Well, I mean, one other little thing I'll just unveil. So there was our answer for this guy, right? I guess that stuff here, maybe I can do. I'll just put that over there. There we go. So there's another example. Okay, so what's going to happen if I calculate I squared? If I is equal to the square root of -1, what's I squared equal to? What happens if I square a square root? What does squaring a square root do to the square root? It cancels it, doesn't it? So what should I squared equal then? If I is equal to the square root of -1, I squared equals what? -1. Strange, huh? Right? Because all I'm doing is I'm canceling that radical. So we'll come back to that. That's an important point. We'll come back to that soon. Okay, so let's finish our problem over here then. We started this example, but we didn't finish it because we didn't know how to deal with that square root of a negative number, but now we do, right? We were just isolating x by using inverse operations.
Attention seniors, your announcements have arrived and they are in the main office. Please come to see me to pick them up. Also, with the following students, please come to the office.
So what's the negative part doing? But the negative inside the square root simplifies to an I outside, and the square root of 9 is just 3, right? So there's our two answers then, our two solutions. X equals plus or minus 3i in that case. Okay, everybody see that? When are we out of here? Like in a minute? Okay, why don't you go ahead and get your desks and we'll call her good. Oh, get your pens too. When you're getting your desks, get your pens.